In this video, we begin at the Athena Start page, access the results screen, and explore images in a dataset. From the Athena Start page, we select the desired user account on the left. On the Data Loader screen, click on the Results tab at the upper right of the screen. This pop-up menu allows selection of a dataset in a similar way as the main loader screen, either from a user account or by browsing to a network or hard drive location. Again, purple dots represent analyzed datasets and green dots represent images only. For illustration, I will select the purple dot to load and visualize a previously analyzed dataset. When the results screen is loaded, it appears the same as it did after running image analysis. From here, I can explore the images comprising the dataset by clicking on the Images tab here on the left of the screen. If I had selected a green dot labeled dataset on the selector screen, then we would be directed directly to this menu to begin image exploration and visualization. First, I will describe navigation within the Image Explorer tab. Then I will demonstrate how we can interact with the images themselves to create colored RGB overlay images from the black and white grayscale raw images, as well as how to create an image to visualize plate-wide signal changes. Within the Image Explorer menu, we are given a series of tabs along the top, each corresponding to one of the color channels that has been acquired in the dataset. The heatmap present at the top of the screen now serves as a navigation tool to select the well where we would like to visualize images. Below it, we see a button that allows us to turn on and off the visualization of masks that were determined during image analysis. Obviously, this button is inactive when a dataset has not yet been analyzed. To begin, I will turn off visualization of the segmentation masks. Next to this button, there is a plate preview button, which can allow us to look at multiple images across all wells in the plate simultaneously. This visualization tool can be utilized to qualitatively and visually compare a treatment effect across several wells in the multi-well plate. But to enable such a comparison, we must first set constant contrast settings for all images, which is a process I will describe later in the video. Along the main light gray shaded area toward the bottom of the screen is where the thumbnail images are displayed, one for each field of view acquired. Currently, image thumbnails in the blue channel for well G3 are displayed. We can navigate to a different well by clicking on it in the heatmap. Above the color selection tabs, we can see a menu for selecting specific fields of view within the selected well. If we quickly glimpse at a different dataset which was acquired with time-lapse and Z-stack, then we can see the additional menus to select specific time points or Z-slices of interest. When dealing with datasets comprised of many individual images, choosing a subset of the fields of view time points and/or Z-slices facilitates exploration and reduces the number of thumbnails displayed, which makes the generation process less time-consuming. Thumbnails are regenerated when moving between wells to account for changes in their defined contrast settings. Such recreation helps visualize apparently dim signal by setting relevant contrast ranges, as will be shown in a moment. In datasets such as this one that contain many images, we may be presented with a pop-up window asking if we want to generate all of the thumbnail images. Clicking on No gives us the opportunity to select a subset of field indexes, time points, or Z-slices. The status of thumbnail generation is shown as a green bar along the bottom. If it is taking longer than desired, we can click the Cancel button at the bottom right and halt the process. Having described thumbnail generation together with options for image navigation, both between wells and within a single well, let's go back to the first dataset we were exploring and dive into how to look at the images themselves in a meaningful and interactive fashion. By clicking on an image thumbnail, we see it displayed in a new window. Here, we can interact with it in a similar fashion as we did on the analysis parameter calibration screen. In the center of the new window, we can see the image itself, and below it, we see a button to open the pixel intensity histogram. The histogram shows the range of pixel intensity values within the image along the horizontal or x-axis, and account for each pixel value along the vertical y-axis. The large peak on the left of the plot corresponds to background in the image. Clicking on the log button toggles between linear and logarithmic scales of the vertical count axis. With a logarithmic axis, we can more easily visualize the low occurrence bright pixels, which are in fact the signal we want to visualize. We can also use the Show Saturation button to color all of the saturated pixels in red. It is imperative to set illumination conditions during acquisition such that the presence of saturated pixels is minimized or ideally eliminated, especially for experiments quantifying fluorescence intensity. If instead an image is to be used only for segmentation, such as often occurs for nuclei, then it is less critical but should be avoided to ensure good segmentation. We can use the pixel intensity histogram to interrogate raw pixel values within an image by mousing over the pixel of interest and following the location of the vertical blue line present within the plot. The value of the pixel is shown below the plot, here. If I move the mouse over a dark area, the blue line is on the left-hand side of the histogram and corresponds to low intensity values, whereas when mousing over a bright area, the line moves to the right-hand side corresponding to high intensity. The initial contrast setting that we see here is defined using the full range of pixel values present in the image. We can use the intensity histogram plot to manually set the contrast range. Setting contrast ranges allows for improved human visualization of the image and can permit qualitative brightness comparisons between images, but does not change or in any way impact the raw pixel values saved in the image file. When adjusting the contrast range for visibility, we define intensity values for coloring pixels either black or white in the rendered grayscale image. Black colored pixels are equal or less than the lower bound, while white pixels are equal or larger than the upper bound. Again, this is only a visualization and does not change the raw image data. Within the pixel intensity histogram, we click and drag to define the range of pixel values to be displayed. One way to set contrast range is by placing the lower bound to correspond to an area of background, which should appear black, and drag the contrast range upward until we see all the details we're interested in visualizing. Alternatively, we can click in an area we want to appear white, then drag downward to determine what should be hidden in the background. These contrast levels can be applied to other images in the dataset using the Apply to Wells or Apply to Plate buttons, which we see here immediately below the plot. Clicking on one of these buttons will apply the current contrast range, upper and lower, to all images either in a single well or across the entire plate. The contrast settings are defined only for images in the same color channel and do not affect other color channels. We can also remove the contrast settings by clicking on the Clear Thresholds button. Setting a constant contrast range is necessary if we want to visually and qualitatively compare fluorescence intensity across a plate. Setting the contrast range in each color channel is also needed to obtain high contrast overlay images, since the black and white levels set through the pixel intensity histogram are also used when creating RGB color overlay images. I will now demonstrate how this works. First, I will click on the Overlay tab to see the starting point for RGB color overlay. As we can see, both the green and red channels appear quite dim, making details difficult to see. Now, we will set contrast ranges for each color to generate better and more useful overlay images. Starting with the blue color channel, I will set the contrast range to make the nuclei appear bright with low background. Then, apply these contrast settings across the entire plate. Now, I perform the same operation for the green and red color channels. Having set the contrast range for all colors, we can look at the overlay image again and see that it looks better. The relative contributions for each color can be adjusted using the Overlay Definition button. When we enhance the contribution of the red channel, its color becomes brighter and more visibly detectable in the overlay image. It is also possible to change the color assignments for each channel. For instance, I can make the nuclei imaged in the blue channel appear white. By manually defining the contrast range and adjusting the overlay, we are able to improve the overall appearance of overlay images generated within Athena. With the overlay now nicely generated, I can turn the masks on to see the cells identified in this particular image. Mousing over an identified cell will display the attributes extracted for that cell in the area to the right of the image. If I select several wells, then I can click on the Plate Preview button, shown here, and visually and qualitatively compare fluorescence signal across all of the wells that I've selected. With the Plate Preview visualized, we can update the field of view displayed in the preview by using the Field Index menu. We can also show single-color grayscale images by selecting the appropriate tab. In each case, we see the Plate Preview image updated according to what we select. If the contrast settings are not manually defined prior to Plate Preview visualization, then each image will have the contrast range detected automatically according to the distribution of pixel intensities in that image. But, since we've previously defined the contrast settings, we can visually compare them in this fashion. Again, switching to the preloaded dataset having time-lapse and Z-stack acquisition, we can explore the Quick Movie and Quick Montage buttons. These quick access tabs utilize a number of fixed presets for creating movies and montage images. These can be helpful for a quick look at a movie or a montage, but additional features are available for movie and montage creation in the Export Movies and Montage button shown above. Use of the menu accessed by this button will be discussed in a separate video. To show the use of the Quick Movie and Montage buttons, a single field of view and a single Z-slice is currently selected. We see thumbnails for all of the time points present in the dataset. If we click on a thumbnail and visualize the larger image, we can preview the Quick Export Movie by clicking on the play button at the bottom left of the preview window. In the field next to the play button, we can also adjust the frames per second, FPS, of the playback preview. The Quick Movie tab combines these images with their current contrast settings into a movie file. Once export is complete, the movie can be played immediately from within Athena or can be accessed for offline viewing from within the Movies folder created within the Dataset folder. Selecting a single time point and visualizing all Z-slices, the movie created shows the change in image focus as the Z-stack is acquired. Lastly, selecting a single Z-slice and visualizing all fields of view, we can click on the Montage tab to create a montage image together with the overlay of the detected segmentation masks. Moreover, This montage is interactive, with the field of view corresponding to the current mouse position being reported at the top of the montage. In this fashion, we can readily move back to a single image of interest to inspect it on the larger screen. That's all for the information in this video. Good luck and enjoy exploring your image data.